I'm Giuseppe Maggiore and welcome to the third lecture of the Introduction to C# course. In this lecture, we're going to talk about loops. Now, loops are the construct in most programming languages where we gain the ability to perform some statements, repeat some statements multiple times. And the importance of such constructs is truly essential because most interesting problems in programming require sort of searching for a solution. Now, the solution might not be the formal definition of a solution to a problem, but like you keep transforming your data until you reach a sort of a plateau of transformation, after which no further transformation is required. So this sort of dynamic movement towards a transformation step by step until you reach a desired state is one of the foundations of the ability to perform some sort of dynamic reasoning in an abstract space. So, the constructs we have at our disposal for performing this sort of looping are actually multiple. There are many ways to tackle this problem. There are while loops, there are do-while loops, there are for loops, there are for each loops, and it is even possible to use recursion, and there are plenty of functions in the standard library that abstract the concept of performing a sort of iteration. The simplest form of loops are the so-called while loops. While loops look in general like this. We have the while keyboard, then we have a condition, and then we have the so-called body of the loop, which is a statement. Actually, the curly brackets are part of the body statement because we can have just a single statement without curly brackets or a composition of statements with curly brackets and semicolon. Okay. The condition, just like an if statement, must be a Boolean expression. And very similarly to how if statements work, the body may not only contain all the statements we want, but also variable declarations, which will only exist inside each and every single iteration of the body. This way you may define intermediate or temporary variables that are needed in order to compute the next step in the iteration, but after the next step has been computed, those variables are discarded because outside the context of the loop they make no sense. And the main idea behind loops is that the condition will tell us whether or not we have arrived at the desired destination, at the desired solution, whereas the body performs a single step in the computation that gets us closer to the solution we are seeking. So we have the state of the program, then we check the condition. If the condition says yes, then okay, we're done. The state is already good. Well, actually, for a while, the condition tells us whether or not we have not arrived, because if the condition is false, then we're done. S0 was the desired state. Otherwise, we perform the body. The body gives us a new state S1, and then we check again. Okay, is the condition now false? And well, if the condition is false, then the condition is true. We keep iterating. If the condition is again true, we perform the body again, we get a new state, and we get is the condition true again, etc. And eventually the condition ends up being false, meaning okay, do we still need working? Do we still need to perform our computation? But when the condition is false, we have the state n, which is the final one, and we continue after the while loop with the rest of the program. For example, let's say that I want to create, let's say, a sequence of characters which length is always a power of 2. So if the input is 1, I want to create this, well, no, let's actually start with something a lot easier. If the input is 1, then we just create a sequence of characters with the length of the input for now, and so on. Okay, so how long will the sequence be? Then we read the input, so var length will be int dot parse console.readline. Well, we're not really checking for the length for the string to be a proper number, so if someone types in something crazy, this is going to break, but that's an issue we accept. But at least if the input is null, then at least we compensate for with 0. Okay, well, we put 0 as a placeholder. Now we can say, okay, while. Well, okay, first of all, no, we need to build the result. We need to build the resulting string, which starts obviously empty, and then at every iteration until we reach the length, then we add an asterisk. Okay, so var iteration, well, we haven't performed any iteration, so the current iteration is 0, while the iteration is smaller than the length, because we want to take length steps, we add the asterisk to the result, and of course we increment the iteration because we want to keep track of how far we've come. And then we can print the result. Let's run this. Oh no, hello world of, no, let's do this properly. Hello world of loop. So we're done already with conditionals. Okay. How long will the sequence be? 5, and we get 1, 2, 3, 4, 5. Oh, very good. Let's try the edge condition, 0, okay, makes sense. Let's put a silly input, -4, okay. Well, iteration is 0, but because it's impossible to, well, remove characters from the empty string, 0 is already, 0 is already greater or equal than the length, so we don't step inside the while. The while gets skipped altogether, starting from the first iteration. Alright, we could also go backwards and do something a little bit destructive. We could say while the length is greater than 0, and then we decrease the length by 1 at every step. The result is exactly the same. But what we're doing now is we get the length, and instead of adding a new variable that tracks how far we are, we decrease the length in place. This has one advantage: we have one variable less. One big disadvantage is that we're losing information about our application, because now we have variable length, which is collapsed down to 0. So length doesn't carry any more information, and yeah, it's kind of, how can I say, misleading now as a name, because yeah, you kind of expect the length to, well, still be meaningful. But anyway, I've seen this in practice. In some cases it might actually be useful. But let's go back to the previous solution, to the previous version. Okay, so we have the iteration. We can also play around. For example, we could have powers. So we could say that at every iteration we want the length of the string to be 2 to the power of the input. So for 1 we have 2, for 2 we have 4, for 3 we have 8, and so on. So we want to construct exponential strings. Okay, so the result in this case is a single string, and then at every iteration here we say, okay, let's double the string. Result and result. Now when for 3 we do get already the, yes, that looks like an 8. For 4, yes, and so on. Or we could, I don't know, do something funny, create a sort of pyramid. well, a very fast growing pyramid. So how long will the sequence be? For 3, then we... No, this is definitely not what I was expecting. Okay, okay, interesting, interesting. Okay, let's debug this. Let's debug this, because now I was expecting to have 1, 2, 4, 8, one after each other. Let's find out what is going wrong. Let's put a breakpoint here, run and debug, start the debugger. Okay, oh yeah, of course. How long will the sequence be? Sequence will be... Ah, oh, ah, how silly. Okay, no, of course not, because then the result always contains the slash ends at every time. Oh, beautiful. Okay, so we have the result, which will be empty, and we have the current row, which will be doubled at every iteration. So the current row gets doubled at every iteration. Oh, yes. And the result gets the current row appended. Yes, 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 yes. Okay, so we get, well, the result so far, slash n, and the current row appended afterwards. Okay. Wasn't much debugging. Well, I would like the terminal back. Yes, here it is. Very good. Let's try it. And there you go. Okay. Well, better actually to swap them, because we do want the one string at the head. So 3, there we go, 1, 2, 4. Okay, very good. Well, there are 3 steps, so now it's a decision of what do these 3 steps actually mean. So do we want the steps to start at 1? Do we want it to start at 2? Do we want to add an extra step because it's aesthetically more pleasing? Whatever. I do find the initial empty string a bit ugly, so I'm going to say first we put the current row and then the result, so that the initial row is not empty, otherwise we get an accidentally initially empty row. And but no, quite challenging actually. Okay, no, because now we swap them. Let's start with the row in there at the beginning, and now we say that we want to that we start at iteration 1. There's little edge cases to get, you know, also the start condition proper. It always takes a little bit more effort than one would like. This is one of the reasons why programming takes a lot longer than even expert practitioners tend to expect. Very funny. Okay, so very often loops have a given simpler structure. So a while loop, like we've seen, we can decrease the length variable, we can count like we're doing with the iteration. We can do whatever we want. Let me give you an example. We could say that actually we want to stop when the current row dot length reaches the desired the desired length, but the length in this case will be the exp 2 to the power of length, because yeah, every time we expect to double. Let's run this. Let's see if I managed to get it right. Oh no, there is yeah, power of 2 length minus 1. Let's see if this is what we're looking for. Possibly. Yes, there we are. Okay. And yeah, this is actually quite powerful, because now we're not saying, okay, this while loop will take 5 steps or 3 steps or n steps, which is quite easy to reason about and predictable. While loops are unbounded. And the more complex the condition becomes here, the higher the chance that the condition might actually never be met. Think about this. So if here we have in the condition of the while loop an arbitrary condition that might contain whatever code we want, then this code might also never become false, leading to a while loop that runs forever. This sort of infinite loop is one of the big challenges of programming with loops, it's quite a dangerous thing. And that's the reason why, unless we really need the unbound power of while loops, a new kind of loops has been introduced that a lot of people use very, very often in order to have a more structured way of looping. The most commonly encountered loops simply feature a body that needs to be executed a given number of times. And this is super common because when we deal with collections where we have a series of items that all need to be processed one after another, or we know we need to take 10 steps or n steps or whatever, well, we don't need all of this big power. So let's go back to the previous version with the iteration. You can see we have an iteration variable. The condition states that the iteration has to be smaller than, well, the number of steps, and at the end of each of each body execution, we increase the iteration. Well, enter the for loop. The for loop has the following shape. For we have the declaration of one or more variables. These are the so-called iteration variables. We have the condition and we have the step. And obviously in here we have the body. Now, this is the initialization of all the variables that are required for executing the control part of the loop. So usually this is the counter variable that will count the number of steps. The condition checks whether or not we have performed all the steps we want. And finally, the step performs the increment of these loop maintenance variables after a full execution of the body. So we can say for, I'm actually going to pick this iteration variable. I'm going to say, okay, we start counting at 1, that is the case. Then, well, the check that we're going to perform in order to decide that we haven't reached the end of the loop, of the for loop, is still the same, iteration smaller the length, and then the iteration variable at the end of the body simply becomes the step block. Notice that I refactored our while loop into a for loop, and this was intentional to show that this kind of common while loops, basically someone at some point realized, okay, guys, we're all writing the same while loops over and over again, but sometimes we make mistakes. How about we structure and streamline in order to reduce the number of mistakes and standardize a pattern which de facto is always there anyway. And well, let's make sure that we haven't broken the semantics, even though this would be actually quite shocking. No, we haven't. And there you go. One of the side effects of this, though, is that the iteration variable, this one, well, it's not available anymore. This is very important. While loops require all of the variables that we want to have also for the management of the iterations, so counting or administering that the iterations are exactly the right iterations we want before the loop starts. The problem is that after the loop is gone, those variables have no semantic anymore. They really are garbage, and this garbage needs to be collected and recycled. And unfortunately, that just doesn't happen with a while loop because, well, the language has no clue whether or not the iteration variable is still needed or not. It's valid in the scope, you may use it, and as such, it will be kept till kingdom come. In the case of a for loop, though, the iteration variable allows us to also define a sort of intermediate scope. So the iteration variable is defined in the scope of the for loop, but it's also garbage collected after the last iteration. So as soon as this condition evaluates to false, the iteration variable gets cleaned up. Very nice. We can also perform variations. For example, we can count back. We could say, okay, so the iteration starts at length, and when the iteration is smaller or equal than 1, and we count backwards, then we are done. Okay. Obviously, we can also do some yeah, for this example, it doesn't really matter, but for example, if you're going through the elements of a collection and you want to start from the last element of the collection, well, this might actually make sense in your context. You could also do all sorts of things. So you could say, okay, increment or multiply by 2 or whatever. I mean, the kind of steps and the sophistication that you have available in for loops is also quite high, but in practice, for loops really are meant for this very clean, very intuitive semantics of you have a series of steps, take the steps from 1 to 100 and you're going to be there. And for loops are indeed very beloved and very powerful. Just like any other constructs in the language that manipulates statements, because the body we said is a statement, well, inside the statement we can put whatever we want. So we can nest loops and conditionals together. This means that we can have a loop inside another loop, a conditional inside a loop inside a conditional, and so on. There is no limitation, and indeed the ability to combine the idea of this repetition of loops, which allows us to search for a solution, with the ability of conditionals to represent decisions, is actually the basis of what makes programming powerful. Now, so funnily enough, you could literally turn every program, like every program possible, into a while loop with a series of ifs. Like, this is sort of a universal pattern. You would have the initial state, state is S0, and then you keep transforming the state until you're done. I know this sounds insane, but yeah, trust me, the more you think about it, the more you'll find out. This is the universal pattern of programming, but there is a big but to be put here. Obviously, this is worthless in practice. So most of what we do, you could say, okay, you know variables, you know loops. After you know arrays and conditionals, you're done. You know everything there is about programming. Why bother with all these languages and complexity? Yeah, because it's about manipulating complex knowledge domains, and code is a knowledge domain. Code encapsulates knowledge about a dynamic series of processes, so it's really not a joke, it's a serious thing. And structuring code well is the challenge. For the computer, for the machine, it doesn't matter. It can just be a gigantic while loop. But for us, how to structure information, that's quite important. Anyway, I digress. So we can nest things. Let's play around a little bit with drawing stuff on the console. I really like these examples. They are quite trivial, but well, I like the fact that when drawing little shapes on the console, you sort of get a direct translation in 2D of nesting loops with some conditionals. So there's that. Anyway, let's start by creating a little square. Okay, we have our square, and this is going to be our little figure. And then we could say, okay, for we start with, we assemble the rows one after each other. So for each row from 0 to n, one of the nice things of using these patterns, like for loop, is that there are also plenty of IntelliSense powered features that autocomplete for loops in the standard way for us. So that's very nice. And here I can say, okay, the figure will be the figure with an asterisk added to it. And obviously, after all the columns of this row are inserted, we also put a /n, which signals visually the end of the row. Let's say, okay. Oh well, it is how large? How large will the shape be? Okay, we get our little squares. Obviously, if we put 5, then we get a bigger square. Okay, not very exciting. We could alternate now. We could create a sort of checkerboard, saying, okay, we don't always want to have an asterisk. Sometimes we want an asterisk, but sometimes we want just a space. And then we get an alternation of full and empty spaces. Okay, so we could say if, well, okay. Let's start by the column. If the column is even, then we add an asterisk. Otherwise, we add a space. Let's see what happens now. This is not a checkerboard yet. Okay, we get the even column is full and the odd column is empty. Okay, but now what we want to say is that the even columns in the even rows, so if the row is even and the column is even, actually, let's see if we get lucky. Well, okay, this is a bit too much because we want to say the row is even and the column is even, or the row is odd and the column is odd. And there's the checkerboard. Okay, very nice, almost nice, but let's put a sort of border around it because I think that really helps. So if the row is 0, or the column is 0, or the row is n minus 1, or the column is n minus 1, or yes. Okay, let's put something a little bit bigger, so let's say 8. Well, characters in a console are not really the best of the best when it comes to replacing a sort of pixels or squares, but you get the gist of it. Also, you might notice that I very confidently put ands and ors without any brackets. Why? Because and is multiplication. Remember from the lecture on the basics, and takes true and true and gives true, takes true and false gives false. So if we consider true to be like 1 and false to be like 0, true and true is the same as 1 times 1 is 1, and true and false is 0, is false is like 1 times 0 is 0. Whereas or is sort of like plus, because when we have true or false, we know it's true, so it's kind of 1 plus 0 is 1. And false or false is false because 0 plus 0 is 0. That's how I remember it, at least. So that's why I can confidently do this without having to put any brackets. We might simplify this a little bit, but this is just cleverness. So basically what we're saying is that row modulus 2 and column modulus 2 have to be equal because they both have to be 0 or they both have to be 1. So we can simplify this a little bit. And then we can remove this condition. I'm not saying that this is necessarily a good idea, because I don't think it increases the readability of the code. So this is something you need to think about quite carefully, because this row modulus 2 is equal to column modulus 2 is something that you only see after having written out the full condition. So sometimes there might be a strong advantage to just writing out the full condition. And even if it's bigger, even if it's more boring, yeah, this is going to be so much better for the future. So, in worst case, just create a little auxiliary function that performs the check so that you even get a verbose name that that encapsulates this. Or no, not even a function. We could say var is frame pixel. And well, even by the power of variables, you know, when you get something that's too so excessively long that you feel the need to split it up, well, don't split it. No, don't just split it up. Give it a name also. This will be even rows, even columns, and even row. So var is even column on even row, and is odd column on odd row, and it's this condition here. And look, all of a sudden, well, by just giving names to things, you have left yourself a breadcrumb for the future in order to be able to to understand your own code and to refactor it even better by changing its essential components, because we're also stating that these four conditions, they really belong together, they are relatively trivial, they check whether or not the pixel is on the frame, so semantically it's just an operation. Then we check, okay, the even columns on the even rows, okay, and the odd columns on the odd rows, and if you want to adjust this, change it, whatever, it's quite likely that you will have to change this, or this, or this, because, well, these are the sort of semantically related blocks of logic and information. We might also say, okay, but this whole if then else, well, there is quite some repetition between the then and the else block, because those both reassign the figure to the figure plus something else. So there are plenty of ways to optimize this. We could say, okay, the figure is, so we want to exploit the fact that this is always the same. And then here we put a conditional expression. We say, okay, if it's an active pixel, we put an asterisk. Otherwise, we put a space. It doesn't look happy. Parenthesize the condition. No, we have to parenthesize the whole thing. Wait. Yeah, okay. Fair enough. So this is just a form of ambiguity. So the compiler basically is telling us, you know what? If you want to use a conditional expression within a string interpolation, so this dollar string is a so-called string interpolation, you have to put the brackets. Actually, let me show clearly that the compiler is being quite helpful about this. It's saying parenthesize the conditional expression. Okay, cool. So there you go. Thank you, C# for your instructions. Okay. Obviously, you can nest loops and conditionals as far as you want. So you can have a loop with a conditional with a loop further inside, a conditional with loops inside. You can have 3, 4, 5, 20 loops, one nested inside each other. There is no limitation. And, well, programming is capable of representing spaces of thought in multiple dimensions. And actually, let's say that you're representing a system that has to make a calculation related to the volume of a building. Okay, so literally the volume. Well, so you have to go through or you have to go through the floors. That would be, let's say, the first for each loop. For each floor, you have to go through each room, each apartment, sorry, and for each apartment you have to go through the rooms. That's a three-dimensional problem. But if inside each room there are a series of objects, well, then now you have to go through the objects, and now there is a fourth dimension. Because your categorization of information contains 4 dimensions. Okay, that's actually pretty common. And now let's say that there is a time series, so something historical, like for each object you have the history of that object. When was it bought, who moved it, who used it, etc. Now you have a fifth dimension, and in this case the fifth dimension happens to be time. But programming, because it has to do with a very rich categorization of information, is a lot more than just 3 physical dimensions plus time. There are many more dimensions of grouping and categorization, and that's why we need this ability to nest things together. Without the ability to nest things together, we cannot reliably tackle problems in higher dimensions, which is the thing that makes programming powerful and useful, its ability to adjust to dimensions. So programming is fractal in a sense, and it's also the reason why programming tends to be resilient to the introduction of two-dimensional canvases like low-code platforms, which try to push everything in 2D, and it works really well until it doesn't, because your problem has a higher dimension. You want to structure your code in the same higher dimension. But I digress. Thank you very much for sticking around until this lecture. I would say this is enough for now, and well, good luck with your studies so far. See you next time, and bye bye.